Good morning, everybody. So let's go ahead and jump right in. We have a lot to get through today, so let's get started here. Thank you for those who are putting up their answers up on the chat, and thank you, Micah, for that answer up there. So let's go ahead and again jump in. I'm going to keep my camera off for purposes right now because of it glitching. I had last class, it was glitching a little bit, so I'm just going to keep my camera off for right now. Hopefully, I'll be able to turn it on maybe a couple times during the session, but for right now, I'm going to keep it off. So let's go ahead and go through this really quickly. So we're looking at calculating the momentum, and I'm going to change my color. I don't like black. Here we go. I'm going to calculate the momentum of a 0.15 kilogram baseball that is moving at 31 meters per second. Again, units are going to tell us everything on what the variable is going to be. So 0.15 kilograms, is that going to be mass? Or is that going to be velocity? Who can tell me in the chat box? Is that going to be mass or velocity? Good. Thank you, London. Yes, it's going to be mass. Absolutely. Nice job. So it's going to be mass. And then we have 31 meters per second. So what is that going to be? Ultimately, that's going to be my velocity. So there you go. Micah has it up here. Excellent job, Micah. Thank you so much for actually doing the problem. And he has 0.15, which is for my mass, times 31, which is going to be my velocity. And I do get my momentum at 4.6 kilograms meters per second. Okay, meters per second. So nice job on that one. So let's jump over to, now I don't know if I want to call this a social question, but it does have to relate to today's lesson. Obviously, I would never want to see anybody hurt if you were in a car accident. It just frightens me. But again, we don't want to see anybody hurt, but it does have to relate to today's lesson. I don't want to see anybody in a physical fight either. No need to fight. So assuming you don't get in any serious injuries, but do you think it would be scarier to be in a car crash or a physical fight, and why? Again, these are examples related for today's lesson. We wouldn't want anybody hurt or in any of this situation. But a car crash, if you've been in a car crash, it definitely keeps you shaking all day. So Andrew, it looks like you've been in a car crash and does definitely keep you, it is scarier because you're shaking all day. Car crash, yeah, absolutely. I'm agreeing with Peter, with Andrew, with let's see, London on this one. Car crashes are definitely a pretty serious thing. Yeah, exactly, London. You're actually on the right track. What I was going to say is, like with a car crash, you don't know when it's going to happen. It's so random and it just comes out of nowhere. On a physical fight, if somebody comes up and tries to punch you, you're able to kind of jab or dodge their punch and be ready for that next one if there is a next one. And so with a car crash, you don't have that ability to kind of gear up for a car crash. You don't say, okay, I'm going to get in a car crash right now. And even though that you're not really geared up for a physical fight, your body has that response of like kind of dodging something that is coming at you. That's just our natural reaction. If you don't know if it's coming, then our body doesn't have that time to react. So definitely, London, you're on it. Car crashes are definitely scarier. I've been unfortunately in a couple of them, and scary, scary, scary stuff. So I hopefully never you will never have to experience that. But if you do, um, just be careful. That's all I ask. My new drivers out there, people who are learning to drive, just be careful. We want to see you back here, and yeah. Uh, Remember, Class Connect sessions are recorded and distributed for learning purposes. Please do not put any personal information or information of others into the chat box for your protection and the protection of others. Make sure you're participating. It is extremely vital that you are. And please, please, at all means, make sure that you're respectful in class and that you are school appropriate. All right, so let's go ahead and get our attendance. Sorry for being just a tad late here. I'm going to grab your attendance here and put it into the chat box. There is your link for attendance, and here is your word for the beginning of class. There you go. So those are your attendance links and the beginning of class or start of class word. Make sure you get it into the question number 1. Again, please do not submit in your quiz, because if you submit it, then unfortunately, then you've only gotten half credit if you're here the whole class period. It will automatically save on your attendance, so please just kind of put it in there and you can close it out. It has automatically saving. Again, I give it to you for your first 15 minutes of class. First 15 minutes of class, you have your attendance in the chat box, If you are late by some reason or need to leave early, you just leave that portion of it blank and you'll get at least half credit for being in class. Again, it closes technically at midnight tonight, so you have up until midnight tonight to get your attendance word. Again, if you want to do it later, make sure you copy it down and make sure you spell it correctly. That's all I ask. All right, let me go ahead and as you are getting your attendance, again, I will always say once you get your attendance done, go ahead and open up your project 2 or unit 2 project because I will be asking you to do that. If you do, by all means, go ahead and raise your hand so I know that you are ready to move on. All right, I'm going to go through these announcements really fast. It is day 21 of our 60-day adventure. I cannot believe we're in the middle of week of Wednesday, January 6th. We're going to talk about impulse, and we're going to do this through our 2J slides in our Physics Unit 2 drop project. Remember, tomorrow is no live class for science. There is live classes for other classes, but not for science. And so this will be your Unit 2 drop project workday. Okay, so you can finish up on anything that you've done. Make sure if you have project slides you need to finish up on, if you want to drop your egg, whatever you need to do, make sure that you if you are going to be dropping your egg, please make sure that you kind of view the other slides because that you may need to do something for that egg or you may need to do something with your the balls that you are working with. So please make sure that you kind of view the other slides that we have not done yet. We do have one more day, which is going to be Friday, that will finish up our slides, okay? Okay, Camila, just no worries. So with that being said, let's kind of take a look at what we have done and where we're going. Again, tomorrow, Unit 2 project workday. On Friday, we're going to talk about collisions. That's our last topic that we're going to talk about. So yeah, guaranteed that January 11th, which is next Monday, we are going to go ahead and turn in our Unit 2 drop project. So next Monday, January 11th, Unit 2 drop project. All right, so let's talk about what we're going to talk about today. We're going to define impulse, and we're going to understand the equation for impulse and momentum theorem. We're going to complete calculations. And then obviously look at this force times the change in time equals mass times the change in velocity. Don't get all nervous about this equation. It's pretty easy. It was as soon as we start doing a couple of examples. We're going to provide examples of how to decrease the force during collision also. Okay. And we're going to do this all through project slides 33 and 34 in class today. So with that, let's jump right in. Again, I'm seeing a lot of hand raises. Excellent. Go ahead and open up either your Google Slides or your PowerPoint version. Raise your hand as you do that. If you do need, and let me give it to you really fast for those who are doing Google Slides, I do have the link here to open it up in Drive. Okay, in case you are having an issue. Excellent. Thank you, Colleen. I see your hand raised. If you are over here and have not started yet, folks, you should be started by this point, okay? We are turning it in on Monday. So if you are not over here and have not started your project yet, you need to go to your grades tab right at the very top. Go to your grades tab on the class webpage, and you're going to scroll down to Unit 2, and you have two options here, your Google Slides or your PowerPoint version. Pick one, whatever works best for you, and start opening it up and start working on it. If you've been using the alternative method, taking screenshots, photos, and notes, that's fine, absolutely. Just make sure that you get that into your slides in your project, because please do not send us this stuff because will not give us what we need, okay? Now, if you are using the alternative method, please make sure that you are raising your hand so I know that you're with us and participating. If I don't see that, again, 3 strikes rule in here. If I call your name 3 times in 3 different actions, then I will just excuse you from the class today. Okay, we need full participation in class. We need to make sure that we are working and that we are working diligently and participating and paying attention. Okay. All right, so let's check in with a few people because I see a lot of people. So still looking for Dylan, Edgar, Damon, London. It looks like we're working. Daniela, Andre. Let's see. Some of us may have had it open, but thank you so much. May have had it open, forgot to raise your hand. So still looking for Dylan, Edgar, Damon, Andre. Colleen, you're good. Daniel M, Tamara, and Zach. Zach, Tamara, Daniel M, Jonathan, Andre, Damien, Edgar, and Dylan. Thank you so much. Thank you, Jonathan. Thank you, Daniel M. Beautiful. So still looking for Dylan, Edgar, Damon, Andre, and Tamara and Anna. Anna, I thought your hand was raised. If your hand's raised, just leave it there. I'll go ahead and move it down for you. So still looking for a few people. Anna, 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 Tamara, Andre, Andre, Damien, Damon, Edgar, Edgar, Dylan, Dylan. We are waiting on you to hold up your rest of your class. All right, I'm going to go ahead and move on. All right, so let's take a look at this brainstorm here. This brainstorm is, what are some features in modern day cars? There is so many safety features now in modern day cars. It's unbelievable. So many features in modern day cars that can keep you safe during a car crash. So in the chat box, start naming a few of those features there. Who can tell me some features of, yeah, London. You're absolutely right. You know what's funny is my parents have a nicer car than I do, and so they have something called auto brakes too, which kind of that stop automatically. Seat belts, airbags. Good. I'm seeing all that. Seat belts, airbags. And yes, I have tested the waters of my parents' automatic brakes because whenever my parents are here in San Diego, I always take their car around because their car is much nicer than mine. So why not use their gas, huh? Rear view mirrors, rear view cameras. Yes, excellent. Good, excellent. Backup video. It is, what kind of car is, I don't even know. I just know it's much nicer than mine. I think it's a Mazda CX-9, but it has all the bells and whistles. Yes, Micah, bumpers. You know, we have much softer bumpers. Much softer bumpers. So yeah, all of these things are what makes our car safer. Okay, we have, and some of you may have also those lane detectors. We also have blind spot detectors on some cars where it just, when you go and you're trying to merge in a different lane and there's a person in your blind spot, it will start beeping at you and screaming at you. Again, my parents' car has all the bells and whistles, but when you go into the different lane, my dad's wheel starts to shake. It goes, "Arr!" I'm like, ah, what is it doing? You know, I first drove it, I'm like, Dad, what is this doing? What is this doing? But it's because it's telling you that you're going into the different lane, and I'm like, well, yeah, I am. So again, you know, all these different features. I want you to keep that in mind though, as we talk about our topic today. So we're going to talk about impulse. Now, impulse is two definition here. The first definition is a product of the force applied to an object, and the amount of time that a force is applied is directly related in our equation here. Impulse equaling force times delta t, the difference in time, okay, the amount of time. You will see this sometimes just I equals F times T. Okay, but just to let you know that this does mean the difference in time. Whereas definition 2 is the change in momentum of an object. So we're going to take a look at, first of all, at definition 2 and break that down just a little bit. So we need to recall the momentum equation that we talked about yesterday, which is P equals mv. Okay, simple momentum equation, mass times velocity. We know that as an object has more mass, it is more difficult to change its motion, resulting in more momentum. The faster the object is going, it is going to be more difficult to change its motion, so you're going to have more momentum. Okay? So just remember that the bigger the object or the faster the object's going, the more difficult it is to change its motion. So it's going to have more momentum. Now, impulse, the definition 2 is changing in momentum. We're going to break it down just a little bit. If impulse says it's a change in momentum, then it's going to be I equals the change in P, which is momentum. How do I break that down even more? I equals final momentum minus the initial momentum. How do I break that down even more? We know that we can break this down even more because you know P is equals to m times v. So we can say mass times the final velocity minus mass times the initial velocity. And I'm getting it exactly from right here, the momentum equation. Now, looking at this, I can take out m, okay? M is going to be my common variable. So when I can take it out and bring it out like this. So I can have I equals m times final velocity equals initial velocity or minus of initial velocity. Well, again, I can break that down even more into this final equation right here. I equals m times the change in velocity, which this would be my change, okay? My change in velocity. Now, I don't need you to know all of this, so don't panic. I don't need you to know all of this. What I want you to know is where I got this equation from. Where I got I equals m times the change in velocity. Go ahead and give me a thumbs up if this makes sense. Again, I don't need you to know this. I just need you to know that where I got this from. A lot of stuff here. Okay, this is just the second part. Thumbs up. Yeah, I can go over it again. Absolutely. Absolutely. So it's looking up here, London, it says an impulse is equal to the change in momentum. Well, I'm just breaking it down. The change in momentum is going to be momentum, my final momentum minus my initial momentum. Well, if you look over here, momentum is this equation, right? So I'm going to go ahead and just take this equation and break it down. This is going to be my first momentum, momentum times my final velocity, minus my second momentum is mass times my initial velocity. I take out the m because it's a common denominator or a common variable, and then I just go ahead and say m times final velocity minus initial velocity, and this is where I end up. Okay, perfect. All right, excellent. Let's go ahead and move on now. So now let's talk about what we call the impulse momentum theorem. Okay, theorem is just simply we're going to take two things and see how they correlate. What does it mean? So we know that the first definition is the product of the force applied to an object in the amount of time. And so we're going to take this first definition and it's going to be right here. And that's going to force times time is going to equal the change in momentum, which is m times change in velocity. Okay, I just need you to know that this is going to be our impulse momentum theorem. We're going to break this down even more. We're going to do a practice problem from this, okay? But what I want you to know is that force is related to time equaling mass times the change in motion, which is velocity, okay? All right, so with that, let's do some practice. Slide number 32 is this, just to kind of give you a reference, slide number 32 is exactly this particular slide. So if you do want to go back and kind of read it carefully on where I got this, it's on slide number 32. Again, slide 32 is just a reference slide. It is this slide telling you where I got impulse momentum theorem, okay, from the definition 1 and then from definition 2. So let's do some practice with this theorem. Looking on slide number 33. Slide number 33 on the left-hand side, we're going to talk about old and new cars. Okay. Now, old cars may seem sturdier, but actually have decreased crash time. So it takes them much shorter time to hit on impact. Okay. So let's go ahead and see how much force is exerted from an old car with a decreased crash time. Let's break this down. A 900-kilogram old car moving at 30 meters per second crashes to a stop in 0.02 seconds. What is the force of that old car? First of all, 900 kilograms. Is that going to be time, mass, or velocity? Who can tell me in the chat box? Good, Micah. Good, Juliet. Yes, Matt. Yeah, it's going to be mass. Okay, this is going to be mass. Now, 30 meters per second. Again, look at the units. Meters per second. Is that going to be time or velocity? Okay, no worries, Camila. Again, you have the recording later on today. Good, London. Or look at it again, London. Meters per second. Good, Matt. Yes. It's going to be my velocity. Velocity is always going to be meters per second. Yeah, it's always going to be meters per second. Whereas when you say 0.02 seconds, seconds alone is going to be my time. Okay? When you see seconds alone, it's going to be my time. So I have all three things that will help me with my equation. So time, or delta t, was, I'm just going to go ahead and put 0.02. Okay? Mass is going to be 900 kilograms. And then obviously velocity is going to be 30 here. All right. Now with that being said, we want to go ahead and simplify. And the way to simplify is, first of all, we want to simplify the side that actually has two numbers. This side only has one number that has f times 0.02. So that doesn't have two numbers. I'm going to leave that one alone for right now, but I'm going to multiply 900 times 30. When I multiply 900 times 30, what do I get? You actually have to get your calculator out for this one. They're going to be some pretty big numbers. Good, Micah. Yes, Juliet. Yes. I want to see a couple more answers. Good. Yes, London. Yes, Matt. So I get 27,000. Okay. And again, I apologize for my writing here. It's terrible. All right, 27,000. Now with 0.02, I'm just going to bring it down. Okay. Now the whole idea here is that I want to get f by itself. In order to get f by itself, I have to go ahead and take the inverse of multiplication. And what is the inverse of multiplication? What's the operation do I do? What is the opposite of multiplication? Division, right, Matt? So what I'm going to do is I'm going to divide out 0.02 because I want this f by itself. So I'm going to go ahead and put 0.02. And remember, a fraction is simply a division problem. That's all it is. When I divide 0.02 by 0.02, I'm going to get 1. So again, these two things cancel each other out. But what I do to one side, I have to do to the other side. So if I divide it on this side, I have to divide on this side. So I'm going to go ahead and divide by 0.02. Now I can just divide 27,000 divided by 0.02. And what number do I come up with? It's going to be a super big number. Matt's got it. London, try again. Put in 27,000 first and then push the divide sign and then 0.02. Yeah. Good, Andrew. Yeah, no worries. Good, Colleen. Good, Danielle. Yeah, I get 1,350,000 newtons. So I'm going to go ahead and pull this one over here. So I get 1,350,000 newtons. That's a lot of force. That is a big amount of force. So let's go ahead. I'm going to give you just 25 seconds. I'm going to give you 25 seconds to go ahead and plug all these numbers into the left-hand side of slide number 33. All these numbers in the left-hand side of slide 33. Raise your hand when you're finished. But what I want you to pull from this is that this is a lot of force. This is a lot of force. Again, raise your hand when you got all these numbers plugged in. 15 more seconds. All right, so just checking in with Dylan, Edgar, Daniel C. Damien, Ali, thank you so much. I'm seeing people put their stuff. Thank you, Daniel C. Dylan, Edgar, Damien, Ali, thank you, Ali. Andre, Tamara, Zachary, Veronica, Kaylee, Allison. Let's go ahead and get our hands raised. Again, thank you for those who are working quickly and promptly. Nice job. Dylan, Edgar, Damon, Dylan, Edgar, Damien, Andre, Tamara, Veronica, Kaylee, Allison. Let's get our hands raised. Dylan, Dylan, Dylan. Last call. Dylan, Dylan, Dylan. Edgar, Edgar, Edgar. Thank you, Edgar. Damien, Damien, Damien. Last call. Damien, Damien, Dylan, Dylan. Andre, Andre, Andre. Tamara, Tamara, Tamara. Veronica, Veronica, Veronica. Kaylee, Kaylee, Kaylee. And Allison, Allison, Allison. Haven't heard from a couple of people, so I'm going to go ahead and all right, let's go ahead and move on. Thank you, everybody. So remembering this is a lot of force, let's go ahead and take a look at this one. A new car has those crumple zones, which increase the crash time. So a new car with the same mass, so I'm going to go ahead and put the same mass in as 900, okay, kilograms, and has the same velocity, so the velocity was 30, and stops at a 0.15 seconds. So there's my time, 0.15 seconds. Now, knowing from the last equation there, what is the force of the new car? I know this is going to be 27,000. I don't need to calculate that again because 900 times 300, we've already figured that out. The only thing that's different is that 0.15, so I'm just going to bring that down. Okay, so when I bring that down, again, I want f by itself. So I'm going to have to do the inverse of multiplication, which we already said that it was going to be division. So I'm going to go ahead and divide out 0.15. Remember that a fraction is simply just a division problem. So these cancel each other out. What I do to one side, I have to do the other side. So I have to divide by 0.15. So now, go ahead and plug in 27,000 divided by 0.15. 27 goes in first. Push the division sign and then 0.15. What do I get? I see an answer up there. Nice job, London. Nice job. Yes, Daniela. Yes, Micah. Yeah, I get 180,000 newtons. Now, having 180,000 newtons, it's not it's a big number by all means. It's a lot of force, but it's much, much less than 1 million newtons. Okay, it's much less than 1 million newtons. So go ahead and plug these numbers into the right-hand side, and I want you to go ahead and we're going to analyze this problem in just one moment. So I'm going to only give you about 25 seconds to do that because I do want to keep moving. 25 seconds to do that. Hurry, hurry, hurry. Raise your hand when you got that up. Thank you, Colleen. I see your hand up. Thank you, Veronica. I did see your hand up on the last one, so thank you so much. Again, if I'm working too fast, go ahead and take a screenshot, take a picture with your cell phone, and always go ahead and put this in a little bit later. All right, just put it in a little bit later. Just checking in with a few people. I know Micah and Andre, they look like they're working. Jaden, Colleen, you're good. I see you down here. Tamara, Zachary, Veronica, I see you. Excellent. Thank you so much. Kaylee and Allison. Kaylee and Allison. Zachary. Thank you, Zachary. Andre, looks like you're working. And Tamara, Tamara, Tamara. Kaylee, 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 Allison, and Daniel M. Daniel M. Let's get our hands raised. Excellent job, everybody. Thank you for working so quickly. So let's go ahead and analyze all of this. So how did the force compare when the time changes for the same type of collision to be completed? Let's take a look at the old car. The old car stopped at 0.02 seconds. 0.02 seconds is a lot faster stopping and resulted in 1,350,000 newtons, which is more force, okay, more force, and is more deadly. The more time you have, the less time you have, the more force you're going to have, the more impact you're going to have, okay? Whereas if you looked at the new car, it stopped in 0.5 seconds, which is a much slower time. In essence, is a much slower time and resulted in only 180 newtons. That's a much less than 1 million. So it is a less force and it is less deadly. So ultimately what I want you to take away from this is that the less time you have, the more force you're going to have, the more impact you're going to have. The more time you're going to have, the less force you're going to have, the less impact you're going to have. Okay? All right. So with that, let's go ahead and move on. So connections here, when we have from our brainstorm, we calculated or we looked at how um, modern day cars have airbags, padded dashboards, crumple zones, all these different safety features. It's because it's to help increase that time. If you increase the time it takes for a collision to occur, it decreases the amount of force you feel. So that's where we want to make sure that you understand. The more time you have, the decrease in force, and the less impact you will have. Okay? Take a look at these examples here. You have this truck who's going to go into the hay. That hay is going to kind of slow that truck down, so you're going to have a decrease in force. Whereas if the truck was just going and going and going, there was no hay to slow it down, it's going to hit that wall and have a huge impact. It's going to have a huge impact. So that's where we want to see that, what I want to kind of stress to you. So let's look at slide number 34. On the left-hand side, slide 34, when a parkour athlete jumps from a building, it is better for them to land on their feet or do a roll, and why? What do you think? Parkour is, if you ever heard of parkour, you may or may not have heard of it. It's where these people actually like jump over boxes and do a bunch of rolls and stuff like that. There's a few people that actually, there is classes that you could take to learn how to do this stuff. And maybe you've done it, I don't know. A roll is literally like London, a tuck and roll. Like, they will jump over something. Yeah, they'll roll their body. They'll jump over something instead of landing on their feet, they'll kind of like do a tuck and roll. Like a somersault. Yeah. Yeah, so I'm seeing a lot of people up there kind of putting rolls. Yeah, I agree with you. I definitely a roll. Why would it be better for them to do a roll? It does sound a little weird. Yeah, parkour is actually a pretty cool. I think, don't get me wrong, I don't know, and I have to do some research on that, but I think they're trying to get it into the Olympics. Like it's a pretty big sport. Good, Colleen. Yeah, they don't hurt their legs, right? What are they doing with their time though as they are? Good. I see Andrew up there. They're decreasing their time, right? If they decrease their time, they have less impact, right? They have less force. So then if have less force, they're not hurting their legs, they're not hurting their knees, they're not hurting their ankles. Because if you could imagine, how many of us have actually jumped off of a wall or a building, not, oh gosh, not a building, but like just a wall or just a chair, and maybe we kind of lock our knees or kind of lock our ankles and we don't give that bounce to it. It hurts, right? It hurts our legs and it hurts our knees or it hurts our ankles. It's because we're not increasing our time. Oops, let me apologize. That is not right. This one's wrong. It's actually increasing our time. This one's correct. We're increasing our time because then we have less force on impact. Okay? Less force on impact. Excellent. So go ahead and lock those answers. It's do a roll and increase our time of impact. Go ahead and lock your answers in on that one. I apologize, it's increasing the time of impact, not decreasing. We don't want to decrease our time because we want to make sure that we have more time because more time, less force. Raise your hands when you got that finished. Raise your hands as you got that finished. Thank you so much. I'm going to give people just another 10 seconds, 10 seconds. Alrighty. Just again, you're just literally erasing or circling, doing a roll and increasing the time of impact. You can delete the wrong one, Matt. Delete the wrong one. Or if you want to, you can use the tools and box it. It does not matter to me. It does not matter. I just want to make sure you understand that you want to do the roll. That's fine. Cool, London. All right, I'm going to go ahead and move on. I think everybody's got this. So on this one, we're going to go ahead and talk and practice a little bit about the impulse momentum theorem. On the board, in the water balloon, in a water balloon toss, would it likely be most likely to prevent the water balloon from breaking? What will most likely prevent the water balloon from breaking? Is it moving your hands down as you catch the balloon? Or is it keeping your hands completely still? Or is it moving your hands up to meet the balloon? So I want you to kind of think about a water balloon, and I'm going to go ahead and turn on my camera. Hopefully it works. A water balloon is being tossed to me. Am I going to keep my hands rigid and straight? What's going to happen if I keep my hands rigid and straight? Good, Colleen. You're smarty pants. You're jumping ahead. Yeah. If I keep my hands rigid and straight, the water balloon's just going to splash in my hands, right? Because there's no for it to go. There's no increase in time. Now, if I actually hold my hands up to meet the water balloon, again, I'm not increasing my time, so the water balloon's just going to splash into my hands. But if I hold my hands and as the water balloon, and if you ever played a water balloon toss, this is a little hint on how to win it. When you catch it, lower your hands, because as we are lowering our hands to catch the water balloon, we're increasing our time of impact. Increasing our time of impact results in less force, then the water balloon hopefully will not break. So with that being said, with the explanation of that, moving your hands down as you catch the water balloon increases our time and allows for the water balloon to have less force on impact. Okay, on impact. So just remember that as you do a water balloon toss the next time. All right, with that being said, we're going to go ahead and take a look at complete on your own. In a boxing match, when someone is about to be hit, and this is going to be the right side of your of your screen, and I'm going to have you do this on your own, but I'll walk you through this. But when someone is about to be hit, they may relax their neck and allow their head to move back upon impact. This is called riding the punch. Based on the impulse momentum theorem, which two of the following statements explains the reason behind this technique? Well, remember, what do I want to do? Camila, it's all right. What do I want to do? So frustrating. It is completely frustrating. If I want to increase my time, what will that allow the force to do? If I increase my time, so when a boxer punches, they relax their head and their neck, that increases the time. What's that going to do? Is it going to increase the force or decrease the force? Good, London. Yes. So again, when a punch comes to a boxer and they relax their neck and they kind of ride the punch, is what it's called. Ride the punch. What's happening is at the time they're increasing their time and they're decreasing their force. They're decreasing their force. So excellent job, everybody. This is a complete on your own. So you need to go ahead and just complete this one on your own. I'm going to go ahead and move on because of time, because we are losing time, and I want to go through slide number 35. Slide 35 is a project slide. This is to be completed a little bit later, but I want to go through this with you. What would be the force that your object experiences when it hits the ground? When it hits the ground, if it takes 0.002 seconds. That's very, very short to complete the collision with the ground. Well, we know from what we have experienced today is that the less time you have, the more force you have, the more impact. So this force should be pretty high here. This should be pretty high, okay? Whereas if I took my object, what would the force of your object when it hits the ground at 0.02 seconds? That's much longer. My force is going to be much less. Okay, now some of you might think, well, where am I going to get the mass and the final velocity? Remember, I'm going to get the mass from slide number 13. So mass equals slide 13, whereas my final velocity, FV, is going to be on slide number 27. We talked about this yesterday, so that's going to help you with that one. So those are where you're going to find your mass and velocity. Your time is going to be up here, is right here. So then all you need to do is calculate the equation. Okay, calculate the equation. And then again, from what you know already, is if it's very short collision occurs on the breakable object, then this would be less more or equally damaging. If you have more force, it's going to be obviously more damaging. If you have less force, it's going to be less damaging. That's why our cars are made the way they are today. It increases the time of collision, allowing it for less impact and less force. Okay? All right, so let's go ahead and just kind of look at this real quick. This is slide number 36. Again, these slides are what I need you to go through. In order to decrease the force an object experiences in a collision, the length of time that it takes for the collision to be completed should be, who could tell me in the chat box, should be what? If I want to decrease the force, should my time be shorter, longer, or does not matter? Yes, Andrew, excellent. Excellent. It should be longer. Okay, my time should be longer to decrease that force. Excellent job, everybody. So we defined impulse. We talked about the impulse momentum theorem, and we explained how to decrease force during our collisions. And then with that being said, I'm going to go ahead and stop our recording. Thanks for hanging in there, everybody. I know we're over time a little bit, so have a great